Yeah, good afternoon, sir. Good
Sorry,
afternoon,
sir.
sir.
Sorry, sir.
I was just thinking about starting. Then,
No,
okay,
no, no,
sir.
no.
Please go ahead. Please go
So
ahead.
at the outset, I would like to welcome our today's resource person, Dr. Nimisha Vedanti. She is MTech, MSc Tech in Exploration Geophysics from BHU, and she did her PhD in 2007 from Osmania University, Hyderabad. And while working as a junior scientist at CSR National NGRI, Hyderabad, India, she was a DST Boys Cast Fellow at the University of Texas at Austin, USA, where she worked on the inversion of 4D seismic data. In 2016, she was selected for Chair CSR Raman Fellowship, Research Fellowship, and worked at the Department of Geoscience at the University of Calgary, Canada, on the characterization of shale gas survivors in the Western Canada Sedimentary Basin. She has, she had a short research stay at the King Abdullah University of Science and Technology, Saudi Arabia, in 2018 on computational geophysics, and she was the Indian project coordinator for the Indo-Norwegian collaboration project focused on 4D seismic monitoring of in situ combustion process in Balol heavy oil field, India, and feasibility assessment of CO2 EOR process in Ankleshwar oil field. Presently, she is senior principal scientist and in charge of shallow seismic group at SCSR, NGRI, Hyderabad, India, and serving the academic of scientific and innovative research, India, in the capacity of professor. She has supervised 3 PhD and many master students, and she was supervising students from Nigeria under CSR Tawas, and also she also co-chaired technical session during the annual convention society of geophysics USA 2014, and she has published over 60 peer-reviewed articles and co-authored a book entitled Factual Models in Exploration Geophysics, published by Elsevier under the Seismic Exploration series. Madam, with this short, brief CV of yours, I welcome you, madam, and I hand over the mic to Dr. Srinivas sir. Thank you, sir.
Thank you very much, sir. Yeah, madam, before I kind of, give the screen to you, the mic to you totally, I would just like to, just inform all the participants that when we were selecting all our resource persons, we were thinking about what exactly we need to do and all those things. And at that time, we thought, why not, also bring in subjects that are more of interest, research areas that are, explorative as well as adventurous. And these are certain things that the government degree colleges also have to start exploring and start looking into. One of the important things that we have to remember is in the National Education Policy 2020, we are looking at more of multidisciplinary approach towards education, be at UG level or PG level, as well as at the PhD level. With those aspects in mind, we were thinking that, we should also know lots of, different ways of doing research, not only just in life sciences, this science, physical or chemical sciences, but also start to look at how explorative geophysics or earth sciences also work, and what are the research, methodologies and all such kind of things that would go about. So that was the kind of, background that we had when we were inviting resource persons from various fields. As you have just heard, Dr. Nimisha is one of the well-known scientists, and I'm also proud to say that, she is Osmania University alumni, and she did her PhD here with Osmania University. So, Dr. Nimisha, welcome to this session. And as you are aware, this is all about the research process and research design in sciences, and we have participants from government degree colleges. They are the faculty members in the government degree colleges spread all over the Telangana, madam. Thank you very much, madam, for accepting our invitation.
Thank you so much, Professor Srinivaslu. In fact, I'm so glad to talk to the teachers and faculty from Telangana. And in fact, that's an opportunity to sell geophysics to the degree colleges where it is not really taught till now. So thank you very much once again. So shall I start the presentation?
Yes, madam. Yes, madam. You can start the presentation, please.
Okay. Do you see my slide?
Yes, madam.
Okay. So,
Yes.
thank you very much, Professor Srinivaslu and the organizing committee for this opportunity. As already you have heard from Professor Srinivaslu that there is a demand for integration in science and various disciplines of science. So I think I prepared kind of like that, so that a lot of physics, chemistry, mathematics, all these subjects, how those are tied in solving earth science problems. Some issues I am discussing based on that. So I hope that you find this talk interesting. So as you know, that topic is research designing in earth sciences, but since we come from a very specialized branch of earth science which is known as geophysics, the focus of the talk will be more on the geophysics, because I won't be able to do justice with other branches of earth science. But more or less the designing experiment, and then the how outputs are generated, what are the major findings we are going to report, all these are very similar in most of the earth science disciplines, because we are trying to study the mother earth. So the outline of my talk is I'll take this opportunity to introduce NGRI also to the Telangana teachers, and then I'll discuss little bit about earth science, what are the different branches in earth science, what type of research we do, what are the methods we are using, and then coming to the main topic, that how do we design a research problem in earth science. And then I will show some of the examples from geophysics, so that, because if I discuss just the designing, it will be too much of text and all that. So I'll show some of the examples that how we do research in geophysics. And then if you are taking some projects from the government or any other sponsoring agency, there is lot of pressure that your research should be translational. Means whatever you are doing, it in addition to knowledge generation, it should be useful for the society and for the industry. Somewhere a common man should get some benefit out of your research, whatever you are doing. So keeping that in mind, most of our geophysical programs in our institute are not all, but many of these exploratory research programs are turning into the translational research. And then I will discuss quickly in the end of my presentation. So our institute is the National Geophysical Research Institute, completely devoted to the specific branch of earth science called geophysics. But the CSIR, our parent organization, it has a pan-India presence, and all the branches of science it covers. So we do some interdisciplinary science also. We do collaborate with other laboratories also. And you can see we have biological, chemical, engineering, information sciences also. And now the data science also has become an important part of our research. At NGRE, we have different research groups which are basically focused on the earth process modeling. Then we have some groups which are very much focused on the methods which is being used, the methods which are being used for the exploration, like electrical methods, electromagnetic methods. Then we have a complete group for to address the geological issues. They do the geochemical analysis, isotope studies, and then the general geology also. We also have potential field study, thermal geophysics group, and the group which studies the paleomagnetism and rock mechanics for the engineering solutions. The last two groups which I have shown here, seismic and seismology, these are the basically the seismic groups, what we say. The one deals with the earthquake studies, they call it seismology, and the seismic group which I belong to, we do not use the earthquake as a source, rather we use the artificial source. We generate signatures like I would say that in an artificial earthquake, and then we study the earth. So that's why this is the seismic exploration group, not the earthquake or the seismology group. We also have Academy of Scientific and Innovative Research, which take care of all the PhD students, and all the admission in NGRI research program happens through ACSR. And my senior colleague, who also is the coordinator of Academy, will be delivering a talk on 9th, and she will cover some aspects of the mandate and other aspects of the Academy. So I'll skip this one. Now let me start with the very known person. I think all of you must be knowing him, the Charles Darwin, the great scientist, and all of you must be knowing that he was with life science, right? But very few people know that he was actually a geologist. So, and those days, the paper what is shown in the slide, you see this this article he published in 1845. It is like some collection of his notes, not really a specific journal paper. But he was on a voyage for geological mapping, preparing maps, and then he developed interest into different cultures, then different aspects of human life, and then developed interest into life science, and then he developed more theories based on that. But he was also a geology degree holder, and in those days, you see, he had in mind that integrated aspect of the science. He was working on a broader, like a larger issue, not different focus problem. So that concept is again coming back, that you integrate all branches of science and solve a major issue for the society or for industry or for your country. So keep this in mind. I'll sometimes come back to this slide later. Before that, I'll introduce the earth science. I'm not sure if all of you are aware what exactly is earth science, because in school and up to 12th standard, generally what we know is only geography, and which is taught under the social sciences for certain reasons. That's okay, but many students do not think that that's a science subject. And there is so much science involved in that, that without knowledge of mathematics, physics, chemistry, and in fact biology also, you cannot really proceed with good science research. You should know all that. At least maths and physics is compulsory. So in earth science, mostly we study the earth's processes, and that occur inside the earth, because earth is a dynamic planet. Lots of things happen inside that. So we study all that processes, and we also study the processes that influence the external factors from space, or any external factor that doesn't originate inside the earth, that may influence the earth processes. And the earth science is basically divided into different branches, which are influenced from the state of the matter. You must be knowing that the solid, liquid, gas, and we are the solid part of the earth. We study the rocks. And that's what GNG, that is geology and geophysics. So rock study, the solid earth study is geology and geophysics. The liquid earth is the oceanography study. That's also a branch of earth science. The gaseous earth is the climatology and meteorology, and all the atmospheric science subjects that they come under the gaseous earth. We also study the earth's interaction with its neighbor planets and other planets and stars in the space. So astronomy is also for now astronomy is also a part of earth science until it gets again isolated. So all the branches of space science are also for now coming under the earth science studies. What research generally we do in GNG? Because if we study the rock, what is there in that study? Because many people think that, oh, of course rock is there. What is that information, or what is that research you are going to do with a rock? There is a lot to do. We do not really know. We live on the earth, but we do not know what is happening inside the earth. We have very limited knowledge of that. So all the study which deals with the origin and evolution of the earth, the life on the earth, all the landscapes, earthquake processes, volcanic eruptions, glaciers, and up to some extent climate. I would say the paleoclimate, paleoclimate studies also, they come under the geology and geophysics research. Then the 2 points what I have highlighted in the text box, those are the applied geophysics or applied geological problem. These are, of course, the basic part also will be there, but these are basically classified under the applied geophysics, which is exploration and exploitation of natural resources. We do lots of studies to look for the groundwater resources, to look for mineral resources, to look for hydrocarbons, and of course the very precious minerals like uranium, sulfide, or all that. So all the geophysical methods and up to some extent geological methods are also used for exploration of this mineral, the coal gas and all that we study in the exploration and exploitation of that. The groundwater exploration is in high demand because the known reason that all the groundwater resources in country are depleting. So the exploration department in our institute is always overloaded with the projects. We also do the geotechnical and archaeological studies. Geotechnical means whenever a major infrastructure is being constructed, like the metro line, what you see in Hyderabad, or any major construction like the nuclear power plant and all, they need some foundation study that what is there below the basement where they are planning to construct the structure. So that information comes from the geological and geophysical studies. We provide the site information, and based on that, the construction engineers will design the construction of that structure. In archaeological surveys, also the geophysics is used because some hidden tunnels and hidden any structure, there are chances that with some near surface geophysical exploration methods, these structures can be can be delineated. So geophysics is getting popularity in archaeological studies also. We also do study the Earth's magnetic field up to some extent, but that goes as a basic research. But we also, of course, use the magnetic methods for the iron exploration and all. But the magnetic observatory, what we have at NGRA, is basically for the basic study of the Earth and Sun interaction and all. The components what we have in geology and geophysics research can be classified as three. The site work, or we call it the field work. Field work is more common term in geophysics and geology. Any geophysical research problem will have a significant amount of field work. We select a site, we go to field, and then we do some data collection by laying out some equipment in the field areas, and that will continue for sometimes for months. The large field work will continue even for years also, because we cannot do surveys in the monsoon seasons and when there is a crop in the field. So we have to look for certain suitable time in the calendar and then take our equipment, because we need farmers permissions and several permissions will be required. So that's the most complicated part of any geophysical work. The geological field work is not that complicated like geophysics. It's mostly involves some sample collection, or in sometimes the structural geological field work where they try to study the outcrops. They also have to do a lot of walking and then recording, but they don't much deal with the instruments. So laying out and that in instrument wise, the geological fieldwork is quite easy. That and they don't need that much permissions what geophysics instrumentation people would need. And the geophysical field will be a team work, because you cannot handle the equipment, record the data, and do everything on your own. So often it is a teamwork, the data collection in geophysics. But in geology, even a single student can go and do his field work and come back and work for his or her PhD. The laboratory study is more important in geology, because whatever they collect in the field, they try to analyze for the physical properties, for the constituent minerals, to detect the age. A lot of experiments they run in the laboratories in the geology. In geophysics, the laboratory study is optional. It depends upon the aim. Straight away from the field, the data can be sent to the processing centers, and then analysis can be done straight from the field data without really going to the laboratory, unless it is really required. So fieldwork is more important for geophysics, and the laboratory studies are more important for the geology, depending upon the research objectives. But in the end, the computational and desk work will be the third component that is anyhow required, because any analysis you need to do on computers. And for geophysics, it is a very high end computational work, because the huge data we collect, and then we need very like high performance computing system to analyze the data and generate the images of the earth. But in geology, it is not that hectic. It's a simple desk work, even simple analysis would do. And at NGRA, we have facility to carry all this type of work. So the main role of geophysics is, if you see this picture, that that he is a geophysicist, and he wants to know that what is lying below the earth. So the main job of the geophysicist is to decide that what method he or she is going to use to detect this structure which are not seen and which are of importance to for any reason. It might be a fault structure which might generate an earthquake, or it might be some mineral deposit which can be extracted, or it can be a hydrocarbon reservoir. So he has to design a problem to detect the target body. There are various type of geophysical methods. If you see this picture carefully, all these layers are different layers of the earth. And here where you can see a ship, this is an ocean, and this is the land. So geophysical methods can the geophysical surveys can be done on land, on sea, and in fact we can fly also. Our groundwater division and our uranium exploration division, they do fly aircrafts to do the airborne surveys to detect the mineral deposits. Me and my group, we use these type of trucks to and lay out this type of experiment at the top of the earth surface, and we impound earth with some explosive, or we vibrate the earth here, and then the sound waves will travel through the earth, and they will reflect, all the reflection procedure, it's same like acoustic or optics in the physics. So they will reflect back to the receivers planted on the surface, and we record this data and try to analyze, and then try to interpret that what is there on these earth layers from where the reflections are coming back. So that's the seismic exploration job. In the sea, they do the gravity magnetic surveys. Even the seismic also can be done in the sea. Even we can lay out this type of structure in the ocean bottom also. So there are a lot of advances now in the exploration methods. The gravity method can be used, in fact, in airborne, in the land. So in anywhere the gravity data can be recorded. We also use remote sensing methods, the satellite images, to design our field network, to analyze the aerial photographs, to see if there are some structural discontinuities, or if there is any forest area and all that. So we do use remote sensing methods also for detection of structure and selecting the area. The geological survey will be mostly the sample collection, and the geochemical prospecting also, they do the sample collection and then analyze in the lab the chemical properties. And in the standard geological survey, they try to go to the field and see the outcrops, the landscapes, and try to see what are the structures on the surface of the earth. So that's how the field work is very important in the GNG research problems. I have on this funny image for to explain how the seismic exploration survey we do. This is our vibrator which moves, and then we plant lots of receivers which record the reflected seismic waves coming back after hitting the first layer inside the earth. So here I have shown just one layer of reflection, but in practice we have several layers of the earth. So we receive reflection from all the layers of the earth, and that's how we study all the layers at a time by analyzing the data. So these receivers record the returning reflected waves, and this is the seismic source which was moving. This is a plate which moves up and down, and it creates the sound waves which travel inside the earth. And if you see that this is much bigger than a big truck, so the seismic experiments, the seismic research projects are very expensive. These are not very cheap projects that we can take very often. So these projects, that's why, because of the cost of field work and all this equipment, the maintenance also of this equipment is very expensive. So we need mega projects in crores to handle these type of projects. So for every PhD project, we cannot deploy this type of equipment to the field. So we try to acquire more data in mega projects, and then try to do 2 or 3 PhDs with the same data sets. This type of data is required by the receivers, what was shown in that picture. So this is the different receivers. Numbers are there, the different receivers, and the time, this axis is time, and then the amplitude whatever they have recorded. Now, based on this, we try to identify different type of waves. Like with experience, we learn more and more that what different type of waves we are seeing in this recorded data. Like this one is the ground vibration, which is not useful for any of the reflection study. We are looking for the reflections which are coming from the layer boundaries. So those reflections come like a straight here. So they many times in the presence of this high noise, these reflections in the near receivers are not seen. So for that, we use a lot of processing methods. I will explain that later. But once the data is processed, you see a lot of these reflections clearly in the what is happening inside the earth. Those boundaries come clear. And then after interpretation, you see different type of structures. You see there is a discontinuity here, how the surface is changing inside the earth. And we also determine all these colors are showing different properties. So we also determine the property change inside the earth, the physical property change. So this type of outcome is expected from research. And of course, after that also a lot of modeling and simulation will be required. But at least this type of outcome is expected after the research. We also try to correlate with the available geological information, which is shown here, that our whatever in this previous picture, sorry, in the previous picture, what we have seen, these are the impedance. Impedance means multiplication of density and velocity. These are the impedance anomalies, which should correlate with the geological formations, like the thick geological formation, high density geological formation should have the high impedance anomaly. Like that, we correlate with the geology. We also try to detect the paleo channels along with the different structures, different other layers inside the earth. The paleo channels are very important because these were the ancient rivers, I would say, where the lot of sedimentation has happened. So those are very prospective for the hydrocarbon as well as in groundwater also, because if few people have heard that there is a project going on to detect the paleo Saraswati channel, that the main interest to locate that paleo channel is when if that river was existent, it might have recharged deeper aquifers. So if we are able to detect that location of that paleo channel, all those deeper aquifers can be exploited for the groundwater exploration. So that type of project is also running. We also try to estimate the layer properties. This diagram, it shows the permeability. Permeability means how the fluids will flow in any formation. And here you see with geophysical study, high permeability trend is detected in a layer, which will govern the flow of fluids in that river. So that is required for groundwater, that is required for hydrocarbon also when we extract oil from a oil reservoir. Now, having described what all we do in geophysics, I'll quickly cover the design, because any successful experiment needs a good design. So with like any other science, life science or chemical science, it starts with the theory, which is the foundation of the study. Then we identify the participants, collect the data, and then what are the techniques we are going to analyze the data, and the approach, how we are going to interpret the result. So participants and the techniques are very important, because they will govern that what type of data you are going to collect, and do you really have skill to analyze that type of data and run that type of experiment or not. So these are the major components of the research designing. A good design will always provide a mean for obtaining required information, because there should be a measure that how the required objective is going to be met by this design. In the design, we also discuss the availability and the skill with researcher, his team, and supervisor. In geophysical fieldwork, the team is very important. So we also need skilled team. We cannot just have anyone on the team to and send them to acquire the data. Many times this happen that the project leader or the research supervisor is not that skilled to handle that type of work. So that's an example of bad research design, because the whatever we are designing, that should fall in our expertise. The research design should have a very clear objective, and the nature of problem should be clearly defined, and this is very important. That's why I highlighted here, especially in case of geophysics, because we can do different type of researches. We can do a desktop based research, the computational type of research. We can also have a field type of problem. Now if we do not describe what type of problem we have in our hand, then we will not be able to do any planning, because a planning for a field type of project is very different from a computational based project. And I will explain this later. So nature of the problem in the geophysical research is very important. We always make sure that if there is a field component, then we choose our team very carefully. We choose the budget very carefully, because that's where the all problem happens, and that affects the budget and time also. And budget and time are also a part of research design. We should have clear timeline and the budget. If we have that much budget, do we have for this type of study or not? Otherwise we can change the objectives. If we need good funding, the relevance of project in present day is very much important. Like I gave you example in the beginning that for now country is facing this COVID situation. So any good research which propose something related to COVID, that will get funding, rather than if I go and tell that I want to study Himalaya, so that projects will not have top priority this time. So what you type of research you are doing in the present day is important. I can propose a good research on either energy sector, like exploration of hydrocarbon, because we are largely dependent on the import. I can propose a good project on the groundwater exploration, because in summer we always face water problems. So those type of projects will be sponsored, and the researcher also gets visibility. But that's why the relevance in the present day is very important when we design a research. In geophysics, the research designing can be categorized into three types of research problems. And this is purely my opinion, because you might find some other classification also, but this is just my opinion. That in geophysics, we either do the exploratory type of research, or we do the hypothesis based research, or a complete theoretical research. In complete theoretical research, the theoretical development is the priority. And in the end, a new technique will be developed. So this part, my senior colleague, Dr. Kirti, she will cover, because she is coming from a pure theoretical background. I'll try to focus on these two, the exploratory and the hypothesis based. In exploratory research, the field work or the laboratory work, or both, that is very important. That's the priority area, because in the exploratory work we generally go to virgin area, try to find something new, and whatever our data tells, that we are the first to publish, that we are first to say anything about that. So that the field and laboratory, that becomes very important, because we have to put maximum control here, so that the data comes out of the best quality, because we are the first one who are telling anything about this new area. And in the hypothesis based research, the concept is important. The concept can lead to an experiment which you can go to the field, or it can be based upon any existing data set, but the outcome of the hypothesis based research will be a new theory. So in the end, all these three type of research give us new information about the either geophysical techniques or the area. So we get some new information after the research. The in exploratory problems, I can give you some examples from geophysics. Like if we are going to explore natural resources in virgin areas, like northeast area is not yet explored. Large part of our eastern India, the different type of basins are not fully explored. In fact, entire India is not fully explored. Only few oil producing areas are properly explored. So whatever we do in the virgin areas, that becomes a case study and a new research, new information. So this type of problems are categorized as exploratory problems. Only thing is we have to be very careful while acquiring the data, because we have less control on the existing information in the exploratory type of research. The hypothesis based problem are basically intuitive research based, where you have some thought and you are trying to test it either in field or in laboratory, or you can also use the existing data to test your hypothesis. So that can be both experiment or non-experiment based. So for example, I can give you here that in India, we have an hypothesis that the shallow means not very deeper occurring formations of shale, which are younger also, because the shallower will be younger and the deeper will be older. That's how happens in geological formations. So we have an hypothesis that shallower and younger formations can be prospective for shale gas. Um, that can be in India, but in US and Canada, where they are major shale gas producing countries, these formations are older and deeper. So this hypothesis we are testing in the field, whether our younger shales are useful for shale gas exploration or not. There can be another hypothesis that the signal to noise ratio in the data what we collected can be enhanced by adopting certain new signal processing method, which was not tested earlier. So you learn some new, you see some new paper, some new idea clicks on some processing method. So you try to incorporate that in your data processing algorithm. So this second point may not need a new data acquisition. You can reprocess the existing acquired data. Similarly, if you know that there is a new technique which can help you to design the network, design the survey network, and it will enhance its detectability. So that's also an hypothesis, but now this third one has to be tested in the field. So this is how the hypothesis-based problems are classified. The theoretical problem can be any development in from the present scenario. API is acquisition, processing, and interpretation. These are the three branches. These are the three components of G&G studies: that data acquisition, data processing, data interpretation. So any development from the present scenario can qualify as a theoretical problem. Like you develop some new algorithm for migration, which is imaging of the earth, or you develop some new equation to establish relationship between two important parameters, or you develop new understanding of any of the earth process. So these all become the theoretical problems. The research outputs can be qualitative or quantitative. The most of the exploratory problems, since we have less control on the existing information, they end up with the qualitative research, the qualitative output. What we can do is we acquire the data, we process the data, we interpret it, and then we try to present a case study of that based upon whatever data we have in hand at that time. So it is a basic interpretive design where we do not try to quantify too many things, because we do not have lot of control parameters to control lot of physical properties. But the quantitative type of research, it's a kind of quasi-experimental design, where already some experiment is done and you are trying to modify that, and you are trying to quantify more parameters from the existing data set. Like I can say that if I go to area and just generates a layered structure of the earth, and tell that these are the 5 layers here and these are the basic properties of that, so that is a qualitative research. But in quantitative, I will try to do more correlation with the geology. I will try to estimate how the physical properties are varying inside the layer, and I'll try to quantify, I'll try to give numbers to as much accurate as possible to those physical properties in the quantitative research. So, having said all that, maybe you will better understand if I share the real research problem. Say, this is the research problem which generally we do in our institute, and this comes under either the hypothesis based or the exploratory work. This is not a theoretical problem, what I'm going to discuss. So here we want to map certain geology. We want to locate certain buried bodies. Maybe you can say some ore bodies, the minerals or sulfide ores, you can say. And we also want to obtain the 3D image of the subsurface using the geophysical data. That how the earth looks like at that depth using the geophysical data. So the key to solve this problem is to find a physical property of the object that is different from that of the surrounding material, which means suppose if I am planning to locate a sulfide ore body buried inside the earth, so I should know a physical property define that ore body which is different from the surrounding area. Then only my geophysical method will detect it. If everywhere everything all the physical properties are same, then geophysical methods will not be useful, because what we look is for anomalies in the physical properties. So anomalies are good for us, and the physical properties what we try to look for, the basic physical properties, there are many. So the basic are density, the wave velocities, which you can say the sound wave velocities, primary and secondary, the magnetic susceptibility, and the electrical properties. So these are the rock properties what we try to look for. And if any of our target body is having a different physical property than its surrounding, then it becomes very easy to detect, and the anomaly will detect that. So that's why the anomalies are good. Once we decide that, suppose as I said in previous, that my plan that I want to detect some sulfide ore body. Now I know that sulfide is a high density material. So there are two surveys which are sensitive to the density. One is the gravity, because gravity is straight away related to the density of the body. And second, seismic also is sensitive to the density, because in seismic what we see is the acoustic impedance contrast, which is the product of the wave velocity and the density. So indirectly it is also related to density. So if I want to locate a sulfide ore body, I'll plan a seismic or gravity survey. So like this we decide that how which survey is going to help us. Now once we decide the survey based upon the physical property of relevance, we try to design a methodology that how to acquire the data, the least noisy data, and in the most efficient manner. And budget and lot of logistic issues also play a role, because when we go to remote areas where we do not know how the landscape is, whether we'll be able to touch each and every point of the selected area or not, or there will be a large data gap and all. So that those things generally we see from the satellite images, but when we go to the ground, go to the field, there are some different scenarios also. So we try to do the best possible planning for the best possible data acquisition. And before moving to the field, we also do modeling and simulation on our computers to like simulate the entire data acquisition. And we see that what will be our realistic expectations from this type of study. We try to put as many as obstacles in that, and see that what will be the sources of noise in that area, what will be the problems we are going to face in the data. So the modeling and simulation is also important. The data collection starts with the instrument testing. A large number of equipments are required, especially for the seismic exploration. But if we are doing the gravity and magnetic survey, the equipment is very less. Only gravimeter and magnetometer and with some accessories will be required. But seismic data acquisition is a very big instruments game. We also do the topographic survey. So because all this data acquisition, whatever we do, that is in reference to certain geographic locations. So some company or some contractor will do the topographic survey for us. They will provide us the elevation information and the locations of the each point where we are acquiring the data. Then the standard data acquisition starts, where you see this is a seismic section which I have shown earlier. Once this section is generated in the field, we do some quality check whether we are able to see some reflectors or not, because mostly what we see is the noise. And then if sometimes we also do the borehole and the laboratory data acquisition also, but that depends upon the objective of the research project. The data processing is very like acquisition is very important part of the of the seismic exploration. Especially in gravity and magnetic, the data processing is kind of very straightforward. They just try to correct the data for some errors. But in seismic, it's altogether different, big science. In fact, one PhD can be done only on the data processing methods. So what we try to do in seismic data processing is we try to identify all type of noises coming in the recorded data. And deconvolution, I will explain that this is one of the most important process. And the velocity estimation, because output of any seismic experiment is a velocity model of the earth. So to estimate velocities accurately, our processing should be done properly. And deconvolution is a process where we try to remove the source effect. As I have shown you earlier, that we are using artificial source. We are impounding some energy in terms of source pulse inside the earth, and these are the different layers of the earth. They respond like different reflectivity, which is like a measure of acoustic impedance, which is product of density and velocity. So to know what are the earth layer, we need to know the reflectivity. For that, we need to remove the source signature from the recorded seismic trace. So that's what deconvolution does. And all this noise processing, that is a big workflow for that. I'll skip that, but it's a huge work and very high computational work. Once the data is processed, we start interpretation. So this was the section I have shown earlier, the interpretation section, in which the process data is interpreted for different geological and geotechnical objectives, whatever our objectives are. So what we should focus is to estimate the physical properties and their distribution. We also try to gain some geological understanding based upon the physical property distribution. So we try to see different layers, what are the different properties and how they are occurring, and then we try to say that what is there in that layer, whether there is an oil pool or this is just a rock, there is no oil inside that. Of is there any structural discontinuity? All those type of decisions we try to make after the data interpretation is done. But there is a problem in all the geophysical method, that whatever interpretation we do is non-unique and there are always ambiguity. Because what happens that whatever anomaly we see, that can fit to a number of models. So now here comes another aspect of research, that we have to discard the not suitable model based upon the prior information, or we try to put as many constant as possible and try to formulate an inverse problem. So that's how the other models are discarded, and finally one model is chosen based upon different constraints. But again, the finally chosen model cannot be a unique one. Ideal outcome should be once the data is interpreted, we generally try to correlate the interpretation with whatever alternative information we have, and it should match with that. We also try to make sure that our results agree with rest of anything else that is known about that area. And after the research, a judgment must be made about the effectiveness and completeness of the result and their impact upon the geological, engineering, or geophysical question, which was the objective of the problem. Whether we have achieved that or not, a judgment has to be made. Sometimes this happens that we try to go for some exploration and we find our methodology is not that useful, because suddenly we entered very hard rock formation and seismic flows are not penetrating. So we can make a judgment that my source was not suitable, my design was not suitable to reach to the target layer. And if it is all success, we try to develop a mathematical model as an aid to interpreting geophysical survey result. So final outcome will be a Earth model, a 3D model, either a complete model or for the target area with different physical properties. In geophysical research, the person are very important, because that's why I have kept this as a slide. That the same many points are same for other research areas also, that they should enjoy, any person working in geophysical research should enjoy technical and engineering work. But not everyone loves the engineering work. When you take instrumentation to the field, sometimes it doesn't work, sometimes it's because of heat or because of some other manhandling something happens. You should be ready to address the engineering issue also. Then our alert and analytical mind, because many things are unexpected in the field which were not simulated in the computers. So an alert and analytical mind is very much important. You should take a sudden immediate decision on spot while acquiring the data. Okay, this is not working, I change my source wavelength, I change my source parameters, I change like this. Then the person should definitely enjoy physics and mathematics in practical ways, not just on pen and paper and just doing the equation without understanding how it will be applied in the field. That is really must. And whenever, especially when I select students for my problem, I make sure that they understand the physics of the problem, what they are trying to understand, because they are going to see physics in the field, in the real earth, not on just board or in the computers. They also need good written and communication skills, because when they go to field, there is lot of communication required where with the people who do not understand your language, with the district authorities to obtain the permission. So the communication skill is equally important. And sometimes they have to work independently also. Mostly it will be team, but sometimes it happens that they have to take, like when a decision taking problem comes, sometimes they have to work independently also. And the most important is they should be willing to work in remote areas, because most of the geophysical areas are remote areas. And that's how we face many times problem that many students join and then they say that I have this issue, I have family issue, I have this sickness, I can't go to field. So that time it becomes a problem. That field is kind of very important. But of course, if someone has a genuine reason, we try to put them on the computational work in the lab, in the processing, don't send them to the field. So, in the end of all this research, the knowledge creation is the main aim of any research project. So, this is true for any branch of science, not just earth science. And as I said in the beginning, when I showed that Charles Darwin's picture, that in fact, Professor Srinivaslu also mentioned in his introductory address that the time has come for interdisciplinary perspective towards dealing with broad spectrum of scientific domain. We cannot work in isolation. In last century, there were several focused research problems, focused research groups were developed for certain reasons. But now, if you want to handle some bigger issues, the interdisciplinary science must be promoted, and that's how the new age sciences is demanding. And in most of the GNG researches, we do work very closely with the stakeholders, the oil industry, the mineral industry, the geotechnical, like the Nuclear Power Corporation of India, like this, who are interested in geotechnical problems. And we make them a part of our research, because if a knowledge is created by interaction with the different stakeholders, it becomes more translatable. Because nowadays government of India and all the agencies, they are insisting on any research that should be translatable and that should reach to the common man. And at NGRA, there are new research trends we are adopting now in this year, that all the receivers, what I have shown in the seismic acquisition, we are trying to switch them to the with the optical fiber cables, and we try to see that if there can be a cost optimization, because all those sensors are very expensive. So if the optical fibers can be used, then the lot of money can be saved, and the faster layout can also happen. We are also using the electromagnetic methods for the groundwater exploration, and this is addressing the social issues at large, and lot of aquifers are being mapped by the groundwater group using the electromagnetic, by they fly the aircraft and then record the data and try to map the groundwater bodies. In my group, we are focusing more on the exploration of the unconventional hydrocarbon, because everyone knows that we are hugely dependent on the crude import, and now there is so much instruction from the government, we should reduce our imports and all. So the unconventional reservoir, the unconventional hydrocarbon, we have plenty. We have many coal fields in India, in which the coal bed methane and the shale gas can be explored. And that's a kind of hypothesis-based research which my team is doing. And we are also adopting to new technologies in data sciences. We are getting into the high performance computation and the artificial intelligence based methods for the seismic data processing and interpretation. Not just seismic data processing, in fact, other geophysical data also are being processed by using the AI methods. So that's all. Thank you. You can ask me whatever. I hope it was understandable.
Thank you, madam. Yeah, it was. Yeah, you tried to, kind of, bring in the perspective of earth sciences into what we are thinking about the sciences as such. One of the major challenges that the government degree colleges have is the focus on geology and earth sciences related thing is little weak in the GDC setup. So although it is none of our participants kind of headache, none of my headache also, but the commissioner office of the commissionerate collegiate education, they are also focusing on how best we can kind of increase more of awareness and bring in more of students or more of programs being offered, courses being offered in such earth sciences domain. Yep, the session is open for participants to interact with Dr. Nimisha and Dr. Nimisha and get clarification if needed.
Or any query, means if anyone is interested.
Anything that you wanted to know about earth sciences, or you can ask Dr. Nimisha about how her what you say personal career projectile happened, and how all such kind of things. You are all teachers and you have to kind of interact with your own students. If your students come and ask you questions, then you would be able to answer. So yeah, ask questions now. I see that nobody is eager to ask any questions. I don't even see anybody putting up questions in the chat. Yeah, this is mainly because most of my participants, as I just mentioned in the beginning, are coming from life sciences, coming from physical sciences, chemical sciences, mathematical sciences, and all those things. And most of my participants might be also thinking that it is like, okay, what is this earth science, and we don't know anything about it, and why how come we can ask a question. Ladies and gentlemen who are participating in this particular induction program, faculty improvement program, you have to remember that this is what happens when we are kind of given a new situation. This lecture brought you a new perspective, and we are like at loss. We don't know what to ask, we don't know how to interact and all such kind of things. And anyways, I see that there was one question Mr. Dayanand is wanting to ask. Anything, Dayanand?
Good afternoon, good evening, sir.
Good evening,
sir,
please go ahead.
Good afternoon, sir. In our college, we are having minerals, sir, museum of different minerals present in it. So the museum was developed somewhere 30 years back. We are protecting them, that's all. We are making them as a specimen to see, and what is the research we can do there, madam? Our is a chemistry department, and nearly 50 to 100 minerals are there.
Okay.
Specimens.
Okay, if it is a museum piece, then maybe you should not touch it, because that might have been kept under some protected condition for the. Can you hear me?
Yeah, Mr.
Yes,
Dayanand, yeah, mute yourself so that you can listen to her carefully. Yeah.
So ideally, the museum samples we do not touch for any of the analysis, but the chemistry is really important for any geochemical study. So whatever our geochemistry people they are trying to do, they try to like what I know from my subject, that the chemistry group in our geology building, they are trying to estimate the organic content in the samples that we bring from the field. So that's how the chemistry people are helping us in analyzing. Then I have also worked in very close contact with the chemical engineers when I was working on the reservoir, that oil recovery enhancement, in which the requirement was to bring the CO2 um, pressure so low so that it while injecting it doesn't damage the reservoir formation, the reservoir rock. So what was happening, that the pure CO2 had very high pressure, and that with that injection it was, there were chances to damage the formation. So the chemistry people helped us in designing a fluid. They suggested a combination of different hydrocarbons, and in chemically synthetic fluid was designed to mix with CO2, and that reduced the injection pressure. So chemistry can be used in in lot many ways along with the in any of the earth science research. Like nowadays the carbon capture is the most catchy research topic. If you can work on that, and then you can also collaborate with NGRA for because we are not into capture, we are not into chemistry. So if you can suggest some method for using chemistry for the capturing, we can go ahead with then the geological sequestration, or its sequestration in the oil reservoir or any other geological formation. So lot many things can be done in the mineral geochemistry, in the geochemistry lab, but that touching the museum piece I would not suggest you,
Yeah,
but you can visit.
Thank you, madam. Thank you, madam.
Yeah.
Good afternoon, madam. This is B. Srinivas Gaud, Assistant Professor of Physics, Sangareddy. Yeah, my question is that, madam, will you predict regarding the earthquakes while very before it happens, and what kind of analysis you will consider? Which kind of parameters you will take in estimating that earthquakes, madam?
Actually, that's a very common question being asked to our seismology group. Whenever they make a presentation, everyone would be interested in knowing whether they can predict an earthquake or not. But the answer is no. When still now the science is not developed that much that you can predict the earthquake. But yes, some forecasting can be done based upon the historical earthquake data, and then we also try to study the stress accumulation in different active regions, that how the stress is changing. But again, that's like a very vague interpretation of that. Nobody can give you an exact date that this time the rocks will release the stress and the earthquake will happen. What we can do is we can tell you that in which area you can have the high amplification, which can be more damaged. Based on that, the seismic hazard studies can be done, like how the building safety standard should be, what is the safety for this area. Everything depends upon in which geological location you are, how your rocks are strong, how much stress they have, or how much stress they are building under different process. So that can be done, but predicting an earthquake is really not something can be done as of now.
Thank you, madam. Madam, one more question is that, will heavy building construction of heavy buildings and heavier things will they lead to earthquake like that, madam? Is it? May I know regarding that, madam?
Not really, because see, that's why the foundation studies are done. That's why this all the metro line and all, whenever before constructing those pillars, they did all those subsurface studies, that what will be the effect of that construction, and if there are any chances to get into any ruptured area or any problematic area, they change the construction plan. So generally, a construction will not do any such damage. But suppose if you are constructing a dam and there is some pore pressure buildup because of fluid, and the dam is in some active area where there are faults, like I'm not sure if you are aware of the Koyna dam, which is in Maharashtra. So some earthquakes started happening after the dam was constructed. So that is that's a possible scenario, but that's the effect of the fluid, not the dam construction.
Thank you, madam.
Madam, one question.
Yeah.
Madam, actually, we are belongs to life sciences, but my question is, before 4.5 to 5 billion years ago, when the Earth was origin,
Yeah.
so many minerals were present on our Earth. But after this 5 billion, during these 5 billion years, due to the rains and due to the rains mainly, due to the floods, these lot of minerals are washing out, and those are included in the oceans or seawater. Those are not coming back to the earth once again. For example, phosphates. So the phosphate element is very important to the organism. So my opinion is, if that phosphate mineral is decreasing in the soil, then what happens? The organisms are mostly impacted. Then what will be the future if the phosphates like minerals are decreased in the soil? Of course, in your research concern, I am asking.
Well, this is certainly out of our research concern, but means see the what to say, that we are on a dynamic planet. So if you see the constitution of our atmosphere, even the gases are changing in our atmosphere, and somehow our life is also getting affected. We are living in more polluted environment than our ancestors lived. So maybe there is a way of adaptation. I don't know, because you are better people to tell that. Or some technology might be developed, like for this climate, what we are telling, that we are trying to capture CO2 and then inject it inside the geological formation in order to save the, I mean, to get rid of this global warming and climate change issue. So similar type of study for soil replenishment, maybe it should be there, but maybe I'm not the best person to answer this question.
Because why I am asking this question is, because the phosphate is formed from the weathering process from the rocks.
Yeah.
That's why I'm asking. This is mostly related to your subject, I think. That's why I'm
But
asking.
see, weathering has not stopped. Weathering is in happening, and it's in the same pace what was. And of course, there are some cycles where it happens faster, and sometimes it is slow. But weathering is happening. It's not that it has stopped.
It will
If,
not be stopped.
yeah, yes, Mr. Swami.
Sir.
Yeah, if I might just try to, give you a perspective,
Okay, sir.
we have to just remember that all the living organisms, from our point of view, from the life sciences people point of view, we might be thinking that, okay, I got your question that says that, because of surface runoff and all those things, the phosphates are being leached out, and they are getting and deposited into the oceans. If this continues for another billion years, then there would be no phosphate left for life to survive. So that is what the question is, right?
Yes, sir.
Yeah, the very simple answer is, you have to remember that when we are talking about phosphates that are bound with living organisms, the phosphates are there within the living organisms, and when we are dying, or when the living organisms die, they go back to the earth, and that is where the phosphates are released, and again it is being taken up. So whatever phosphates are needed for supporting the life system, living system, they would be there. It would not be like, living organisms will become extinct because phosphates have become extinct, because the required phosphates are being cycled, right? Among the living organisms, although there would be a very short duration wherein they phosphates are getting into the decaying material, and then again it is being absorbed and all such kind of things. So I don't think that, as madam was rightly pointing out, that the ability of living organism to adapt itself to the changing environment is going to determine that, how we are going to, go forward in a scenario, in a theoretical scenario. In future, if at all there is no phosphate available, then what would happen? The living organisms that are totally dependent upon phosphates have to go down, and that means that extinctions would be happening. And those of us who are those living organisms that have the capability because of mutation, etc., to go for other than phosphate for their changes and all those things, support system and all those things, they would survive. And as Charles Darwin has said, survival of the fittest, then only those organisms that can survive without phosphate will survive, and the life will go on. Yeah, or else, yeah, we don't know how the life on Earth is going to get short or get cut off because of any geological or cosmological event. But as long as the life support systems are available, the life is going to adapt itself and change itself. So I hope that I have given you some perspective from life sciences point of view. Madam, there was a question from Mr. Venugopal. All of you don't mind me because your names are just coming with, as I'm seeing on the chat, and I'm not able to go through your, the degrees and all those things. So you might be Dr. Venugopal or not, I don't know, but please bear with me. And Mr. Venugopal has asked us that my area of research is solid mechanics. Data analysis is done by MATLAB. Is there a scope for this field in experimental research? Usage of MATLAB for data analysis in experimental research.
Can you please repeat that? I think the first part I did not hear.
Yeah, he says that he is doing research in solid mechanics. He comes from physics, I believe, and he says that data analysis is done by MATLAB. Okay, MATLAB software he is using. Is there a scope for this field by experimental research? He just wants to ask maybe that experimental research analysis or can be done based on MATLAB software or not?
Yes, it can be done, but we have to formulate a research problem based upon, but it can be done, yes.
Yeah. Mr. Venugopal, I think that, that was your question, and I think Madam has given a clear-cut answer to that. And there is another question by somebody, KS. What are the research facilities or scope for research for life sciences at NGRI? That's a wonderful question.
Actually, our sister lab is there, CCMV. In fact, for our life also we are dependent on them. But in NGRI, we have started a branch called biogeophysics. So, and of course, there is one more section in which we are doing some microbiological studies, where these microorganisms are being injected into reservoir to enhance the oil production. So that for that I think 2-3 years back we did hire some students from biology background and microbiology background. So if someone is interested in these branches of life science, they are most welcome. If some openings are there.
Yeah, that's a good answer and good suggestion that you have given, Dr. Nimisha. There was a suggestion by Dr. Sujata, Miss Sujata, and she says that there are many microorganisms that are present in the soil that are capable of phosphate consumption and rotation of phosphates, she was also of the opinion that because of chemical pesticide and insecticide use, these microorganisms are also becoming, their populations are also getting affected. So her suggestion is like, the reduction of pollution with respect to usage of chemical pesticides and insecticides, and trying to increase such beneficial microorganisms that might be a kind of solution. That's a very, very wonderful perspective that Ms. Sujata has given. And so all of us who are with the life sciences backgrounds and other than life sciences, you can start thinking about how we call it as bioremediation. Bioremediation can be one of the best ways to mitigate the problems that we foresee or we think that in future it might happen. So that's a good suggestion. Yep. Any more questions? I would just like to suggest that, from the interactions that we have got until now, some of you might be interested, some of you who are not coming directly from the earth sciences, because most of us are not from the earth sciences, might be interested in taking care or starting some kind of, small projects or understanding or creating interest among the student community to work on earth sciences by interacting with them, etc., etc. You are aware that Osmania University has good, departments that deal with earth sciences. We have Department of Geophysics, we have Department of Geology, we have Department of Applied Geochemistry, and we also have a center of explorative geophysics. So those of you who are interested, you can either directly contact Dr. Nimisha. Her contact detail is right there on the slide, or you can get in touch with us, and we would also be helpful. Dr. Sri Nagesh himself comes from the earth sciences background, so you can also interact with Dr. Sri Nagesh. Not only that, I would just like to tell you that tomorrow also by this time at the same session 3, we would be getting one of my colleagues, Dr. Srinivas. He is from applied geochemistry, so he would be also. What I'm trying to tell you is, like, you also have people in the university and as resource persons who would be able to help you in case you have any other lingering doubts or lingering questions that you wanted to ask today. If you are not able to ask, you can ask tomorrow. There is no issues, and anytime you can get in touch with Dr. Nimisha and other experts who are available both at NGRI as well as at the university. Yep. Okay. There is a question by Mr. Aravind Tirumala. Is asking, what are the programs of NGRI for soil conservation? Do you have any programs on soil conservation or soil studies, etc.?
No, no. That's actually our interest starts below the soil layer. So
Yes. Yeah. As far as the soil conservation and other things are concerned, it doesn't come into the purview of the research purview. Let me put it that way. Under the research purview of the NGRI as an institute, NGRI Institute, as Madam has rightly pointed out, has a mandate to do surveys, research on different aspects, that is subsoil or below the surface of earth. What minerals and what kind of things happen below the surface of earth. That is what the mandate is. But as far as the soil conservation and all those things are concerned, I just see that the Ministry of Environment, Forest and Climate Change is responsible for soil conservation. And I don't see any other ministry is responsible other than the Ministry of Environment and Forests. Now, again, what type of soil conservation activities that these ministries or these the departments under the ministry, especially the forest department under the ministry, is doing? You might be knowing that India is going through a massive afforestation program, and at the same time, India is also looking for soil and moisture conservation programs, also SMC programs. We call it as SMC programs, and we see that lots of activities are happening with respect to soil conservation. But at the same time, when we are talking about massive afforestation, we are digging up the soil and the soil is becoming loose, and in that particular year, if we have good rain, then as Swami and others were sharing, you would be having surface runoff, and with the surface runoff, the fertile soil as well as other the soil that has been dug out, loose soil, will just be washed off from the place where they were originally there. So I see that it all becomes our collective responsibility as academia, as researchers, as people who are literate, let me put it that way, to kind of educate the society or try to create awareness in the society about soil conservation. Mind it, nobody excepting the forest department is doing anything with respect to soil conservation. If anybody else has any remark about it, you are welcome to add. Okay, yeah, there's a thank you coming out there. Any other questions to Dr. Nimisha? Or general questions? You don't have to worry about earth sciences and all those things. We are all scientists. We are all teachers, right? So we can take up any questions if you feel that you can interact with us. There was one question earlier which I don't know whether I have asked you or not, Dr. Nimisha. It is by Mr. G. Malikarjun, and he is asking what lab facilities can we avail at NGRI?
Is he from any degree college?
Yeah, most of our participants are from the degree college, madam.
Okay. So means they can go through our NGRI website. All the facilities are mentioned there. And for teachers, the procedure is not that complicated. He just has to write to the director NGRI, and then he will provide with a small proposal that what exactly they want to do. Then for students and teachers, these things move. Many times these are provided free of cost. In fact, there are some programs going on at NGRA with different degree colleges and school, where some training also, especially that is happening in the earthquake studies. So some training is being provided for their own protection and for the quick action and all. So it's very much possible that they can access the lab or send their sample and the work can be done here. They just have to approach the director NGRA, what exactly they want to do with that. That's all.
Yeah, I suggest that most of the prospects of research and collaboration can be done by going through at least the website of the institutions that you are interested in collaborating. Try to understand what exactly they are doing, whether that those works, those research works or academic works fit your requirement or not, and then start, as madam has said, start right from approaching the director or whoever. Sometimes some institutions have contact persons for research collaborations or academic collaborations. You find out those contacts and contact them. As it has been said, you will not be given unless you ask. So you have to, if at all you are interested, then you have to go forward and shake hands to collaborate. I have got a question. One question: can we take a picture of earth layers using X-rays? I think if this is Dr. Rajkumar, Dr. Rajkumar is asking, can we take a picture of earth layers using X-rays?
The electromagnetic method, the way it works, it's like X-ray only, that they send the electromagnetic radiation in different frequency ranges, and up to what depth you can go, that will decide that what wavelength you are in electromagnetic spectrum. So if you want to go for a deeper image in that electromagnetic spectrum, you have to be in the low frequency range, then only you can penetrate the deeper. If you want to if you just want a very near surface picture, then in that electromagnetic spectrum you can choose a high frequency spectrum, and then that's what is the basis of the electromagnetic exploration, that a spectrum is chosen and then the source is impounded inside the earth and the image comes. So it's pretty much similar like X-ray, I can say that.
Thank you, madam. Yeah, there was one very quick question. I'm just wondering that whether this question should come to the life science teachers or should go to Madam Nimisha. And the question is, to what depth of earth can we explore microbes? Until what depth the microbes are known to occur? Dr.
See,
Nimisha, if you have any.
what I know, I don't know if this is the right answer or not, but I worked in the heavy oil field, and I know the process of generation of heavy oil is microbe based. They are responsible for the occurrence of heavy oil, and that reservoir was 1 kilometer or slightly more deep. So wherever we get the heavy oil, there are some 2-3 kilometer deep heavy oil reservoirs also, where of course I have not worked on those. So I can expect that up to that depth, definitely they are there. But beyond that, if they are, means they have penetrated or not, I don't know that.
Yes, madam. Yeah, as you have rightly pointed out, the microbes responsible for heavy oils, wherever the layers of the heavy oils are there, that's the deepest, in a sense, that in the Earth's crust we can think about. But yeah, sometimes this kind of questions are also tricky questions, in a sense that if we are looking at Earth's crust, then the Earth's crust, then we think about these things. But if at all we have to find out how deeper than this, Earth's what you say, sea level or something like that, then in the oceans we have almost about 8 kilometers. Mariana Trench is almost about 8 kilometers, and there also we have seen the microorganisms being present. But believe me, this is in the aquatic or ocean ecosystem. They are not in the Earth's crust. So
Yeah.
yes, yeah. So that is what you have to remember. So sometimes it is, if you're talking about the depth of Earth, it will be uh, safely not more than 2 kilometers or something like that. If you're talking about below the surface level of Earth, then almost about 8 kilometers also you will see microbial activities in the Mariana Trench. Yeah, that's a wonderful question. Uh, yeah. Uh, Okay, I would just suggest that if at all you have any more questions, you can just write to us or get in touch with Dr. Nimisha directly. She would be able to help you out, and we'll close the session here because it's already 3:30, and by 3:45 the next speaker is going to join us. What I would like you to do from now onwards is, like, one of the participant is going to present the formal vote of thanks to the speakers of each session. So I would request one of the participants, not somebody, one of the participant, to kindly propose the vote of thanks before one last question, which is kind of being posed by one of our resource person, who is also sitting and listening to the lectures since morning. And Dr. D. Ashok has asked, he has just suggested, is it yeah, it is a question. He says that I heard that petroleum will exhaust by say 2050. Yeah, Professor D. Ashok has asked, petrol will exhaust by 2050. Is it true?
No.
No, yeah, it cannot be. It is.
That's what we are doing, trying to explore some new resource. We'll be out of job.
Yeah, I know. That's a safer way. And if at all there are some people who are saying that the petroleum reserves are gonna exhaust and all such kind of things, it is only the business gimmicks that people are making. It is the political pressure that people are wanting to bring in and all such kind of things. I don't think that the what you say, the petroleum reserves are that restricted. We have not explored lots of places. We have explored only the what you say, less than 10%, madam. 10% of the
Yeah, yes. And then another thing is, whatever reserve we have explored, out of that also we have not produced more than 30% or
yeah, that is
35%
right.
some.
Yeah,
So,
so
and there is so much hydrocarbon in the unconventional which nobody knows right now how much is there. So
yes.
2050 is too close.
Yeah.
So I don't think that is going to happen.
Sir, you are unmuted, sir. Sir, unmute yourself, sir.
I'm sorry. Very observant. Right. So, yeah, what I was saying is till at least 2080 to 2100, we might not be having any problems. If at all we listen to these kind of problems wherein we have, somebody saying that the underground or petroleum reserves are getting exhausted and all those things, it is like, there's a business tactics, to tell you very frankly. There are many places from where we can explore, and also we have so many alternatives, as Dr. Nimisha has said. So who is ready to propose the vote of thanks for Dr. Nimisha Vedanti? Dr. Rajkumar is there? If nobody is going to come, I'm going to, pick one of you. Dr. Rajkumar, yeah, please go ahead.
Yeah. Good afternoon, everyone. Indeed, it was a great presentation and a very fluent, very extremely good presentation from your side, ma'am. You gave great insights about geological science and its various applications. We are very happy and privileged to listen to your talk, and we are immensely benefited by your presentation, ma'am. Hope everybody enjoyed along with me. So on behalf of all participants and UGC-HRDC, and I thank you very much from the bottom of my heart. Thank you for this opportunity.
Thank you. Thank you so much.
Thank you very much, Dr. Nimisha, for having joined our program and having shared your experiences on the earth sciences, how beautiful the earth sciences research is all about. Hope we are going to get in touch once again, and we'll be inviting you again for earth sciences programs.
Thank you.
Yeah.
Thank you.
Thank you very much, madam.